Right then, in this video what we're going to do is look at the mechanisms in chem2, namely they're going to be alkenes. We'll take propene as our example and we'll react it with bromine, with HBr and also with sulfuric acid. Once we've done the mechanisms for that one, we'll then look at haloalkanes and look at the mechanisms for that reacting with hydroxide ions under two different conditions, and also cyanide and then with ammonia. Okay, and we'll use 2-bromopropane as our typical haloalkane. Alright, so let's start off, and by the way, this is going to be a quick summary of these mechanisms. It'll include the essential features of each of the mechanisms, which is quite good. So let's have a look at alkenes first of all, and we'll start off with adding bromine. Okay, so note that the name of the mechanism is electrophilic addition. Okay, so now when you do mechanisms, you need to show curly arrows, and a curly arrow like that will mean the movement of 2 electrons. Okay, you must also show the partial charges where necessary, and you also have to show a lone pair of electrons with a negative charge if possible. May not always be a negative charge, but at least show the lone pair of electrons. Okay, like that. So include these things in your mechanism. Right, so let's start off with adding bromine to an alkene. This is important because this is a test for an alkene. Alkenes decolorize bromine water, so brown to colorless. Right, so let's see then what happens. As the bromine molecule approaches the double bond, we get an induced dipole occurring in our molecule. So we get delta plus there and delta minus there. Electrons are repelled down like this. Okay, right. A pair of electrons comes out from the from the double bond here, and in so doing repels these electrons to the bromine. Notice my arrow here exaggerated slightly, and notice where it's coming from, the middle of the bond. Notice where this arrow is coming from, the middle of the bond. Okay, and notice where it's pointing. So you've got to make sure you get the arrows correct. Okay, so let's see what the result is. We get an intermediate first. Oh, there should be another hydrogen there. Alright, intermediate first of all, where one of the bromines has added. Now you can add anywhere, makes no difference. I think here when we add HBr it will make a difference. I'll explain when we get there. Okay, so we have a positive charge on this carbon atom, and then the Br minus over here that was formed will then go on to attack that positive carbon to make our product. 1, 2, 3, and we've got Br and Br there. Okay, I won't draw all the hydrogens in, but you've got the essential procedure for how the mechanism works. Okay, that's addition of bromine. Let's go on to the next one, which is addition of HBr. Now again, the hydrogen bromide comes along towards the double bond. Now this bond here is already a dipole, so delta plus, delta minus. So put that in to get your mark. It's a permanent dipole. Right. Pair of electrons comes out to meet the hydrogen, and the bromine will take the pair of electrons from this bond for itself. Okay, now there's two possibilities. Hydrogen adding first either to this carbon, the middle one, or to that one. Let's look at both intermediates. Now for the sake of speed, I won't draw all the hydrogens in. Right. So it's added here. There it is, meaning that this will be the positive charged carbon, or the other possibility is where the hydrogen will add here, leaving this carbon to be positively charged. Now this intermediate is the more stable, right? More stable. It is the secondary carbocation, and that's more stable than the primary carbocation. Okay, this will form the major product. This will then go on to form the minor product. Okay, let's have a look then for this one. A Br minus with its pair of electrons, and arrow comes from the pair of electrons to the positive carbon. There we are, forming our final product. Here we are. That. There's the H and there's the bromine. So we get 2-bromopropane. This will be around about 98% product, and the other one will be about 2%. It's a minor product. Okay. There we are. So that will be the major product, all due to the intermediate, which is more stable. Okay, let's move on now to the next mechanism, which is addition of sulfuric acid. Okay, again, the sulfuric acid molecule comes along towards the double bond, the pair of the 4 electrons here, 2 pairs of electrons, high negative charge, and that also may cause this bond to become polar, may induce a dipole here. Okay, but there may already have been a dipole here because oxygen is attached to the hydrogen, so this bond is probably already polar. Okay, let's just put the lone pairs on there. Okay, one more, and pair of electrons from the middle of the double bond, like so, to the hydrogen, and then this will then drag away a pair of electrons. Okay, now remember where the hydrogen adds to the carbon which already had the most hydrogens on it. If you come back to this one, right, notice the hydrogen which added to this carbon here. There we are, look, added to this carbon here. That gave you the more stable carbocation. So if you could sort of have a shortcut way of working out where the hydrogen adds, the hydrogen will add to the carbon which already has the most hydrogens. This carbon's got 1 hydrogen, this carbon's got 2, so the hydrogen adds to this one. Okay, right, so this hydrogen will add to this carbon here. It's got more hydrogens than this one, adds to this one. So then we will get, let's just draw the major one, that's what we're going to get. So here's the intermediate. Okay, there's our hydrogen that's added. Show the intermediate, secondary carbocation, alright, and then the hydrogen sulfate anion will then attack this carbon here. Notice where my arrow is coming from the pair of electrons. Notice where it's pointing to the carbon, so keep that as accurate as you can. Okay, and then it'll produce this thing here. OSO3H, propyl hydrogen sulfate. Okay, now if you was to then add water to this, dilute it, just add water, then that will give us an alcohol. Okay, so 1, 2, 3 OH, where the hydrogen sulfate was. Now for this part you won't need to know the mechanism, just know that adding water will produce the alcohol, and it also produces the sulfuric acid back again, which shows that the sulfuric acid must have been a catalyst. Okay, right, let's go to the next part then. Those are the mechanisms for alkenes. Let's now go on to the mechanisms for haloalkanes. Start off with adding sodium hydroxide. So it's the hydroxide part which attacks the haloalkane. Okay, now the conditions are important. Cold aqueous conditions and sodium hydroxide will produce this kind of mechanism. Okay, right. Remember what you have to do is put the lone pairs where you can, and also the dipole, delta plus, delta minus. In this case, the bromine is electronegative, meaning that this bond here, the carbon-bromine bond, is polar. Okay, pair of electrons comes from there to the carbon, and at the same time, from the middle of this carbon-bromine bond, the arrow comes to the bromine. So the bromine takes a pair of electrons away. So we have this. That's now OH. There we are. I'm not putting the hydrogens in, but you should do that in your exam. Put all the hydrogens in. And there's the bromine that came off. So what's happened here is simply that the hydroxide has substituted for the bromide. So we get a straightforward substitution reaction. Also, the hydroxide is positive loving, so it's a nucleophile, and so we call this mechanism nucleophilic substitution. Okay, let's make a note of that. Nucleophilic substitution. There we are. Okay. Right. Now, if we change the conditions from cold aqueous solution of sodium hydroxide to hot ethanolic sodium hydroxide, in other words, still a solution, but you warm it up, and you will also add ethanol to your mixture, then you get an entirely different mechanism. Let's have a look. Okay. Oh, before we come to that, let's just stick to the hydroxide substitution. Just wanted to say something about the carbon halogen bond strengths. The carbon chlorine bond strength is the strongest, then the carbon bromide, and then the carbon iodide. So that's the weakest, right? Carbon I is the weakest bond, therefore most easily broken. Okay, so if you was to add hydroxide ions, cold aqueous solution of sodium hydroxide to 3 beakers, okay, of chloropropane, bromopropane, and iodopropane, to each one of these, right, and then you waited for the reaction to happen, it's the carbon iodide, the iodopropane bond, the iodopropane molecule, which would react fastest. Now you might say, well, how can you tell? Well, inside your beaker you would have silver nitrate, right, silver nitrate solution. So that's already in these beakers. Now as the hydroxide substitutes the chloride or the bromide or the iodide, then the silver ions will then go on to react with the chloride, the bromide or the iodide, and producing for you the precipitates: silver chloride, silver bromide, and silver iodide. So where you see the precipitate first, you know that that reaction was the fastest. Okay, right. Okay, so this is a good way of actually looking at the rate of substitution with different halogen atoms attached to your haloalkane. Okay, right. Let's move on now to the hydroxide under these conditions, hot ethanolic conditions. Okay, now we get an entirely different mechanism where we get like this. I'll show you. We get a reaction where just before we do that, let's just show the polarity of the carbon halogen bond. Okay, delta plus delta minus. Right, this time the hydroxide will come and try to snatch away a hydrogen from the next door neighbor carbon to where the bromine is attached. So any one of these carbons, any one of these hydrogens, or any one of these hydrogens just next door to the carbon bromine, right? That'll take that away. Now when that happens, the electrons from the carbon hydrogen bond will fall between these two carbons, and at the same time the bromine will take the pair of electrons here, right? Now be careful with the arrows that come from the middle of the bond. Can you see? Middle of the bond, and from the pair of electrons. Okay, now this will produce this here. Let's just show you. Right, we have a double bond there now. There we are, and the bromide has come away, and the OH and the H will make water. Okay, that bromide will join up with the sodium or the potassium that was with the hydroxide, sodium hydroxide, potassium hydroxide. So there we are, like that. And you have made yourself an alkene, propene. Okay, and that would be useful because you could then go on to polymerize your propene to make polypropene, or your ethene to make polyethene, etc. So it's a way of making polymers. Okay, and this reaction is called an elimination mechanism. Okay, what's been eliminated? Well, I'll show you. Right, the water has been eliminated from, so a small molecule has been eliminated from a large molecule. Hence it's called an elimination reaction. All right. Okay, let's go on to the next part. Okay, this time we're reacting cyanide ions with your haloalkane. Right, so mechanism again. Perhaps you could try this if you pause the video and try this mechanism. Okay, well, let's do it then. So delta minus delta plus. Okay, and you have a nitrile. Okay, now the nitrile is the functional group, so that will be carbon number 1. And if you look at this, you've got the longest chain. The longest chain is this one here. Let's say that one there. Okay, so you can call this a propane nitrile. Propane nitrile. Okay, so it's that bit there. That's the longest chain. Right, 1, 2, 3. Hence propane nitrile. And on the second carbon, you have a methyl group. So it's going to be 2-methyl propane nitrile. Okay. Right, next mechanism is with ammonia. Okay, similarly, let's see what happens here. Label the polar bond, delta minus, delta plus. You got the lone pair on the nitrogen. Okay, and the arrow comes from the lone pair, remember, curly arrow to the carbon. Okay, at the same time this bromine takes the pair of electrons from this bond. Okay, there we are, and then producing this thing here. Let's have a look. So we've got, I'm just going to draw this again with that arrow. There we are. So it's producing the N. I'm just going to draw this out. The ammonia. Okay, there we are. When you draw these diagrams on your exam paper or in homeworks, etc., draw it out fairly large, show all the bonds nice and clearly, and the arrows as well. Exaggerate the arrows slightly so that they can be seen clearly. Okay, now this ammonia, oh, there's a bromine, the bromide. There we are. There it is, and that's in solution. Okay, right. The ammonia, you can see from here, has now 4 bonds. 1, 2, 3, 4. It's lost its lone pair of electrons by datively covalently bonding with the carbon. Okay, now it would like to have its lone pair of electrons back. Too many bonds. It only wants 3. So what happens now is another ammonia molecule will come along and snatch away a H from here. Let's have a look how that works. Okay, so we've got NH3. So this mechanism is in 2 parts really. There we are. That and brand new ammonia molecule comes along and takes away a H. At the same time, the electrons from this bond will move onto that nitrogen to replace the lone pair and also extinguishing that positive charge. Okay, so let's have a look at the product. So we have now CH3, C, NH2 now. There's a lone pair back on the nitrogen, and there we are. You now have made yourself an amine. Okay, can you name the amine? 3 carbons. Second carbon has the amine group, so 2-amino propane. Okay, and the NH4 plus, that's that one here, becomes NH4 plus, and you got bromide ions. There they are. So you could have ammonium bromide as the ionic compound formed. It's all in solution as well. Okay, anything else? Yep. Okay, so that was the mechanisms then for alkenes, and also for haloalkanes. Okay, right, we'll stop that one there.